I'll talk about using non-JavaScript code or libraries in JavaScript. Just before that, two things. I apologize for the resolution of the slides. My laptop has been giving me some technical difficulties. Thank you to the organizers of the conference. By the way, you helped me with a few problems. And second point, please feel free to stop me with any questions at any point. I prefer to be asked questions than for you to wait for the end. Okay, so non-JavaScript code in JavaScript. Why is this even interesting? What would be the point? Well, the point is that there's a lot of existing code out there. Maybe it's open source, or maybe you have a lot of code you've written in your company. Typically, it's C and C++. And it can simply be very time intensive to manually port it to JavaScript. You don't want to start writing huge applications from scratch if you don't really need to. Now, the thing is, when you develop a native app, you can reuse that code. So I think we should be able to do that on the web too. It's just a technical problem that's stopping us, really. So I'd like to start with sort of the cool stuff up front, so with some demos. So demo number one, Bullet. So Bullet is a physics engine. It's used actually in several AAA games. It's open source. It's very cool. It's 150,000 lines, and it's pretty complicated because, well, it's a physics engine. You don't want to start writing these from scratch if you don't need to. Because it's so useful, it was actually manually ported to Java, called JBullet. JBullet was manually ported to JavaScript as bullet.js, and there were some demos with this. But there are really two problems with that approach. These ports, since they're manual, they tend to be partial. The people that are doing this, it's a lot of effort for them. They don't port the entire Bullet library as is. They port the parts that they focus on. Second of all, they port a snapshot of Bullet at some particular point in time, so there's always lag. So the trunk version is, I think, right now about 7 point releases later than bullet.js. Well, there are actually 2 manual ports here, so there's double lag. So ammo.js is a port of Bullet to JavaScript with Emscripten, so it's completely automatic. And for that reason, you get the entire library as is, and you get the code in its current state. I have a few links, but since networking isn't working for me, I'll just show you a local demo, which hopefully will work. Okay, so this is a simulation of a few cubes. It's rendering using cubicvr.js. They typically fall in a bit more interesting pattern. So again, this is Bullet running on the web in JavaScript. You might have seen this demo before. What's cool about this right now is that it's actually possible to tweak the demo in interesting ways. So this is being used from JavaScript. So for example here, num is simply the number of cubes. I can change that to, say, 20 and just reload the page. And since it's JavaScript, you immediately get a slightly more interesting result. This is actually a case where it's much more fun to do this in JavaScript than in C++ because you need to rebuild your entire project just to change some parameters. So you can do that, and you can also change things like, let me see, reset positions is the JavaScript which defines where the bodies begin. So let's change the X position to, say, I. So I is the index, the number of the body. If we just set it to I, it should just drop them in a line, I think, if I remember correctly. Yeah. So just sort of falling like that. And just another example, we can make them fall from a higher distance as well. Let's see something else slightly. So it's pretty much the same, but they're falling from a higher distance. Okay, so that's first demo out of 3 that I wanted to show you. Second demo is SequelLite. So SequelLite is a very popular open source database. It actually could have become part of the web through WebSQL, but there's the long quote here that explains why there's a problem with the standardization process. I leave the quote as is, I don't comment on it. But I think the point that I'd like to make is that the issue with standardization is that you need to get people to work together on a specific API, on a spec. But if you just compile the code as is to JavaScript, you don't need to convince anyone of anything. You can just compile whatever you want, and it'll run in all web browsers out there. So here's a work in progress demo of SequelLite. The resolution is making it a bit hard to read what's happening here. But basically, well, this is some quite boring SequelLite code. It'll just create a table, create some stuff in that table, and do a select from it. If I hit execute, you'll get key equals 2, text equals second item, which is what's expected since we asked for the case where value is equal to 987, which is what's over here. So we have that, and of course, I can do additional commands. I think I called it stuff. So if I do that, I get all the elements. The resolution is a bit annoying. And where, thank you. And of course, I can do basically anything else in the SequelLite syntax. If I ask for less than 100, I get just the first item since the others had larger values. And I don't want to type this from scratch, but here's an example of a join between two tables. So actually, it's easier to read it here. So again, it's creating another table, more stuff, inserting some values, and then it does a select, which does a join over the value element. So I'm just going to copy that and run it. And this is the expected data. There were 2 items for value equals 25. So the text first item is from the first table, it's unchanged, and then there's 2 texts from the second table, more stuff, and yet additional stuff. But again, this is just to show that you get the entire SequelLite language by compiling the entire SequelLite implementation. So that concludes demo 2. Demo 3, Python, Ruby, and Lua. These are popular dynamic languages. Actually, because they're so popular, there are several projects to manually implement them in JavaScript. But these suffer generally from the problems that I mentioned before about bullet. These ports are generally partial. They don't implement the entire language. There are a lot of corners in these languages they don't bother with. They lag behind the trunk version of the language. And worse, in this case, they typically target a slightly modified version of the language. For example, pajamas for Python translates Python more or less as is into JavaScript. So you end up with the semantics of JavaScript. For example, if you do some operations on numbers, you'll get the behavior JavaScript has, not the behavior of Python. So you're writing something that looks like Python, but it's not really Python. On the other hand, if you compile the entire language as is into JavaScript, then again, the benefit is you get exactly what you started out with. So if I could connect in the network, I'd show you this website, which was just on Hacker News, repl.it, which is really the nicer way to show this. It uses Python, Ruby, and Lua with the code that I'm talking about here. But instead, I'll show you a local version of the Python one. So it just prints some numbers, just some random syntax. And it actually does import sys and writes sys.version and .platform. And the version of the platform is simply what was there when I compiled it locally on my Linux machine. It says Apple, and I assume because it was built using LLVM. But anyhow, to sort of elaborate on what I said before about differences with the language, let's say that I think I actually have a code, just so I don't forget. Yeah. Let's just briefly look at this code here. So it does x equals to the maximum possible integer. Then it'll print the type of x and x. It'll add 1 to that, so it's maxint plus 1. Print the type, and then print x to the power of 10. Why this is interesting is because Python's handling of numbers is very different from JavaScript. So if I execute this, so the first value here, this thing is type int, it's maxint. But when you add 1 to that in Python, Python changes that to type long. And type long is not just a long integer, it can be basically any value. So when I do that to the power of 10, you get this huge number over here. So this is exactly the same result that I would get if I were just running, for example, Python natively here. You see I get the exact same numbers in this case. So this is the benefit of compiling it, whereas in JavaScript natively, if I just open the console here, and again, so this is code that does something similar. It takes that max int and then shows it to the power of 10. And of course, the results are very different. In JavaScript, the first number is fine, but the second number is a double. So you don't get the same thing we saw in Python with this. So this just shows that you can implement the real version of Python on the web, getting you the exact same behavior you would get in the console native code version, unlike in sort of a manual port that does not copy the entire language as is. I hope I was clear. Oh, and I did want to do a fourth demo that I didn't plan on, but given that the previous talk was about audio, I thought it might be relevant. So the previous talk mentioned the web audio spec and the Mozilla audio data API. And I think the very valid reasoning given for preferring the web audio API was that it's easy to get to results very quickly. You don't need to start writing the middleware or the libraries to actually see results. But the reason is similar to what I was talking about earlier with the Mozilla audio data API. You have access to the hardware, to the audio hardware. All you need is to actually be able to have a library that creates audio in a convenient way. We have that code. It's written in C++. We just can't run it on the web, but we can compile it to the web. And this is a demo of using eSpeak, which is a speech synthesis engine. Again, something pretty complicated that you don't want to start writing from scratch. And if the connection is working, you should hear something. But I guess it's not working. So that was underwhelming. I actually can't even hear it locally. Oh. The people who are sitting in the front row might be able to hear it. I doubt it. I give up.
Crawl very close to your screen with your mic.
Oh.
Hello, JSConfEU.
Did you hear anything? I think that's as close as I can get. Oh well, again, this was not a planned demo. Okay, back to the scheduled programming. So after showing you some demos, I'd like to talk about the more boring aspects about how this works and how you can actually use it and so forth. So how does this work? The idea is you take your C or C++ code, you want to get that into JavaScript, but you need to go through an intermediary step of LLVM bitcode. So LLVM, the low-level virtual machine, is a compiler project, much like GCC, which can compile C code into native code, but it can also compile into LLVM bitcode, which is an intermediary stage, which the nice thing about it is that it is extremely well documented, and for that reason it's used here. So we translate the high-level, well, medium-level C code into this low-level bit code, and Emscripten then compiles that into JavaScript. So this is the big picture of what happens. But what actually goes on here? So in Emscripten, we try to translate bitcode one-to-one. So on the left here, we have LLVM bitcode, and on the right, we have the corresponding JavaScript. So for example, the first thing here, could you see the mouse cursor? Yeah. The first thing here is basically allocate, which means allocate on the stack a 32-bit integer. In JavaScript, you can do something very similar by just doing var, local variable stored on the stack. Similarly, calling a function with a 32-bit integer parameter here is translated simply into a function call. So this is a native JavaScript function call, not some complicated emulation of one. And the last command is a mathematical operation, adding 22 to the variable 1, and that turns into an add. So for the most part, Emscripten just tries to translate the bit code as is, and that works for quite a lot, but not everything. One issue is that C code typically allocates memory using malloc, etc., and it reads and writes from that memory. You don't just put things on the stack. You have the heap. So we implement sort of a heap variable in JavaScript, which is a single large array, a normal JavaScript array, of course, and it represents the memory space. So heap of x is a read, heap of x equals something is a write, and pointers, x here, are simply integers. So I hope this sort of makes sense. Another complicated issue with the behavior of C++ is that, so we saw on this slide that adding 22 is simply $1 plus 22. But in general, of course, that's not correct. For example, in C, x equals 5, and x divided by 2 gives you 2. It rounds down because it's an integer. In JavaScript, x equals 5, x divided by 2 gives you 2.5. So this, of course, is fixable by doing math.floor, although even this actually is not correct, because this gives the correct rounding behavior for positive integers but not negative ones. But this works in most cases. And there are similar issues with overflows, signs. So C and JavaScript are two very different languages. Their semantics do not match one-to-one, obviously. So much of the challenge in writing a compiler from the bit code, but really from C to JavaScript, is to get all these little behavior differences to make them completely vanish. So there are a lot of details here that I will not bore you with. But I will still bore you with some other more high-level details. So to get good performing code, you really need to generate code that looks like this over here, while and so forth. You want to use native JavaScript loops and ifs. The problem, though, is that when you're compiling this bit code, you get what we see on the left, basically these blocks of code. So block 1, some commands, then a branch to block 2. Block 2 is another series of commands ending with a branch. This is very low level. It's like some commands plus go-tos. It's even lower level than the C code that we started out with. This is the Hello VM bit code. So one of the challenges is to get from this code to something that looks like normal JavaScript loops. And there's a big section in the optimizer in Emscripten that tries to reason about these loops and to recreate them to something, because it simply runs much, much faster with the loops. Without loops, you can emulate go-tos with various cumbersome ways. It's extremely slow with that approach. So it's necessary to do this optimizing step. And a second thing I've already sort of mentioned, var x is a reasonable way to implement a variable on the stack. It's of course fast because JavaScript engines have been heavily optimized for that. However, you can't do that for every variable. For example, if you take the address of a variable on the stack in C, you can pass that to some other function, and of course you cannot access var x in JavaScript in another function. So the optimizer needs to reason about when it can optimize by doing var x and when it can't. Okay, so you've written your code, it runs, it's optimized, but how do you actually access anything or do something with that code? You're running it inside a web browser, not on a normal machine with a file system and so forth. So basically, in Emscripten, we've written standard C system APIs in JavaScript. We've basically implemented the C standard libc, basically, and also POSIX and SDL. Not all of these, but the parts that we've needed. We've written a JavaScript implementation of them that sort of makes sense for the web. So it uses an XHR to load files and so forth. So just as an example of what this looks like, you can set up a virtual file system using some command that we added called fs.create lazy file. So you give it the directory, the name of the file, the URL from where it will actually do the load. And the point is that the compiled code, the C++ code, uses the file system in a completely normal way. You do not need to rewrite your C code. The C code will include standard I/O, do fopen, do fread. But when it actually reads from this file.dat that we created here, the JavaScript implementation will actually do an XHR and load that data. So we've made it so you can use your existing C code, but you sort of hook it up to the relevant things on the web. Okay. So how does it actually look when you try to use this to compile a project? So just one more technical detail. There are really two parts in this project. There's the compiler, which compiles LLVM to JavaScript. This is basically what I was talking about before. It's really just concerned with getting the code into JavaScript in a way that works. So it just gets it there. But the problem is we're compiling this LLVM bit code, which is low level, and we get something that's not easy to use. For example, if the code started as C++, you'll have name mangling. You'll have these crazy long function names that really mean very simple things, but you get them in a mangled form. There's also lifecycle issues. Creating objects and destroying them is not easy at all in the low-level bit code. So you get code that works, and if all you care about is taking a project and running it on the web as is, that's fine, and that's what most of these demos were, except for the first one with Bullet. But if you want to use the libraries on the web in a convenient way, you really need something else, and that's what the bindings generator is. It's the work of the past few months. It parses not the bit code, but the actual header files, the .h files in your project, and generates some glue code to connect things. So I'll give an example in 2 slides that will sort of, I hope, make sense of this. But the idea is, again, that there is a compiler for the bit code and something else that creates the glue code that doesn't look at the bit code, but looks at the high-level headers. Okay, so how does it actually look when you compile something to JavaScript? This is slightly simplified, but it gives you the main picture. So you build your library almost normally. You do make and configure, sorry. So you build the project pretty much normally, except you use a different compiler, which basically just changes some parameters, gets it to generate LLVM bit code instead of native code. Then you run the Emscripten compiler on that bit code. This gives you some JavaScript. You run the Emscripten bindings generator on the headers. This again gives you some JavaScript. And you simply combine those into, say, library.js. So if everything goes right, this is pretty much what the process should be. Let's take a look at sort of a tiny example of how the code would look. So if we have a C++, a library that looks like this, so these are 2 really silly classes. A data class that gets an X and a Y, a processor class that gets data class instances. You would use that on the web basically as follows. You obviously import that script into your web page, and then you can use those objects in a normal way. Data1 equals new data class. So again, that data class in C++ takes 2 integers. In JavaScript, you just pass it 2 integers and things are hooked up properly. You can create a new processor by doing a processor class, and you can call methods on them as expected. For comparison, here's the C++ code. Pretty much the same. So the idea with the bindings thingy is that it lets you use those C++ classes in JavaScript in a way that really keeps the high-level interface there, so you can really use these as a library without needing to mess with any ugliness of the low-level compiled code. Few words about this binding API. So when you do new class and so forth, of course you don't get a C++ object because you can't access that in JavaScript, you don't want to. It returns instead a wrapper object, which encloses a pointer to the data on the heap and so forth. It has wrapper functions on it that convert arguments and make sure everything works. So 5, a number, typically doesn't need any conversion, but if other inst is an instance of a class, it'll translate that into a pointer. And again, it does that for you automatically, so you don't need to mess with it. There are, however, some limitations. So Basically, the issue is that JavaScript and C++ are not the same language. Their semantics are different. Again, we saw this a bit before. So they don't match perfectly. For example, when you create an instance, you must destroy it manually. The reason is that while doing new class creates an instance, and of course it'll be GC'd at some point, the compiled code has no way to tell when that object was GC'd. If we could know that, we would destroy the C++ object at that point in time. But we can't. So you need to do the destroy manually. So this is a bit cumbersome. And there are a few other technical issues that I don't want to waste time on talking about. But again, the issue is that the languages do not match up perfectly. So while you can write code that for the most part is pretty natural and close to the C++, it's definitely not perfect. There are some limits. Some can be fixed, but it'll never be 100% identical. So just to summarize this section about using the project. So the project works well on a lot of real-world code. We've not been interested in working just on benchmarks, but on actual code. So we've ported things like Doom, which sadly they sent to DMCA, so we had to take it down. So Doom, the popular game, zlib, compression, Poplar, a PDF renderer, OpenJPEG, a codec for JPEG 2000 images, which actually I can show you locally, I believe. Yeah, OpenJPEG. So, and that's a JPEG 2000 rendered to a canvas element. So this is a file format not recognized by the browser in a native way, but entirely in JavaScript, it was translated into a canvas image, basically. And getting back to that, FreeType, which renders fonts, and as already mentioned, Bullet, SequelLite, Python, Ruby Lua. So this works on real-world code. But again, just a caveat about that, this is for the compiler, which generates working code. The binding stuff, which makes the code very easy to use, is very new and obviously less mature. So don't expect that to work out of the box as is. Two last points that I think I should make. To port a library to JavaScript, you do need to know the original language that you're translating. It's not a 100% automatic process that you just push a button and you get some code. There are a few cases, they're rare, but there are a few cases where you might need to modify the original source code. So you really do need to know the language, if only just to know that the false positives, that warnings that it mentions to you are false positives. So you can't just compile something you don't understand. We can make this better, but right now it's definitely not there. And while generating working code is straightforward, optimizing the code to get to maximum speed takes additional manual effort. So again, this is something that we can definitely fix, but at this point, you can get code to work typically fast. Optimizing it to maximum speed will take more work. Okay, I have just a few more slides, but I should address something about speed. So you might be thinking, isn't this terribly slow? This is JavaScript. Don't we need native apps, native client, Dart, Java, Flash? If you can't read the rest, it doesn't matter. Don't we need these other things that are fast, and isn't there some problem that even if you get this code onto the web, it'll just run too slowly? So I think there are sort of two parts to this question. The first part is whether JavaScript itself is fast enough or not, and we had a talk previously. And I think we know that by now JavaScript is fast enough. But on the other hand, perhaps this compiler method generates code that is not a match to what JS engines are optimizing for. We're compiling this low-level bit code. Maybe it ends up just being very, very slow, even though it does work. So the answer is no, this actually isn't slow. There are some numbers here. They are all in time slower than GCC-03, which means that 1 is actual GCC native code. And these numbers are all for SpiderMonkey, and TA means typed arrays. So most of the numbers, especially over here in the typed array area, are not bad at all. Between 2 times slower than native code and 5 times slower than native code, with this one sort of more depressing test. But overall, these are not too bad, I would say. In addition, one of the faster ones, dlmalloc, is actually not just a benchmark. These other ones are benchmarks. Some of them are well known, some not. But dlmalloc is actually real-world code. It's a malloc implementation used in a lot of places. So the results are not bad, I would argue. To look at data from a different perspective, so the computer language shootout benchmark site at alias.debian compares a lot of languages. So all the numbers here are again times slower than native code. And you can see, obviously, by definition, C and C++ on top are all ones. Java, pretty close, but there are some places where it doesn't quite get to native speed. Scala, Haskell, and C# are also fairly close. And on the bottom, you have Python and Ruby, dynamic things which are not so fast. And JavaScript in the middle here, this is our data, not from the shootout. I think it's clear that the numbers here are much closer to the languages on top than the languages on bottom. So I think definitely the speed is in a good place. And also, this is without JavaScript engines optimizing for it at all. There are a few minor things that if they did, they could run this specific type of code much faster. So I think there's definitely good reason to believe we can get very, 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 very close to native code. But some notes about that. So the speed can vary greatly between benchmarks. We saw that on the data here from 2 to 8.5. It's not consistent like you see in C, where you pretty much know the performance of the code that you write, at least if it's simple enough. And Java, which had a range of 1 to 3, but at least it's pretty contained. So here we have non-predictability, which is problematic for performance, especially since we have multiple browsers with different JS engines. So you have unexpected speeds in many cases. Issue 2, we have bugs in JavaScript engines that often just lead to slowness. For example, the memory space, the heap variable that I mentioned, which represents memory. So basically every read and write ends up being an access of this large JavaScript array. If that's not fully optimized so that every read from it is a literal read from memory and a write to it is literal write to memory, if you need to do any additional work, for example, if the heap is implemented as a hash map, it'll be very, very slow. So there are cases where JS engines get confused and they decide to implement the heap in a slow way. Also, JS engines have typically been optimized for fairly small benchmarks, and also code on the web was typically quite small. They've not been optimized for very large scripts, but here we're compiling 10, 20 megabytes of C++ code and dumping it on the web, so that raises some issues that need to be fixed. But again, these are bugs and hopefully will be resolved. And on the other hand, we have a lot of things in new features in JS engines that are making code run faster. So type inference, SSA optimizations. Also, as I said earlier, it's possible that JS engines could optimize specifically for this type of code. So with all that put together, I would argue that we're not quite at the speed of native code yet, but we are getting quite close. Finally, I'll leave you with a thought about the future. So imagine that you could just write this. This is Harmony module syntax. Module libc from some place, import printf, printf hello world. But imagine that you could do this for any library in any language. So JavaScript basically becomes a universal language or environment, I guess, where everything can be compiled into it. And because of that, JavaScript can use any code that exists anywhere. Just compile it to JavaScript and use it in a convenient way. So I think this could really be very, very beneficial for us on the web. And again, as an example, just sort of as a follow-up for what I mentioned before about audio, we can compile an entire audio library to C++, to JavaScript, and use that instead of waiting for some for a web audio API to be standardized. The ability to use any code that we want on the web could really help us do whatever we want on the web, which I think is a good thing. And that's it. Thank you. Questions?
Hello. This is like crazy powerful. It's cool. So my first question was more about the kind of fopen support, you know, the kind of like standard file operations where you said you mapped it to XML HTTP request. I mean, are they synchronous or asynchronous?
Well, you could do it both ways. You could do it.
But so
If it's asynchronous, then you would need some way for the compiled code to know when they arrive, which would mean you would be creating a little API in C++ that is not part of standard IO.h.
Right, but the standard one is just synchronous.
The standard one is synchronous,
Yeah.
so the implementation we have now is synchronous, yes. But there's nothing stopping you, again, from implementing a tiny addition to standard IO, which would be asynchronous. And there is a little header which adds a few functions right now. Like, for example, it can let you basically run any script from C++ code just by doing eval.
Wow.
So you can bridge both ways, and you can definitely get asynchronous behavior if you want, but again, it would be an extension of the standard C.
Sweet. Yeah, because I mean, that was the thing I worried about. Was whether... So I can have one more question? Sorry about this. Right. Is anyone writing the kind of the wrapper for web, like OpenGL to WebGL? Because that, I mean, we can get so many games on the web then.
Yes, I would be extremely happy to have that. So a few words about that. There is so first of all, this project is fully open source, of course. It's on GitHub, etc. There is a closed source project called Mandrill, which it uses some amount of code from this project, which I only know because if you look at the compiled code that they generate, you can actually see bits of this in there. However, they say that they wrote a compiler entirely from scratch, so I'm not entirely sure where the truth is. But anyhow, my point is they have what you just asked about.
Yeah.
They have a compiler from OpenGL to WebGL. I have no idea how it works. It's closed source. But they have some demos of games just compiled to WebGL.
Yeah.
I'm myself not an OpenGL hacker, so I don't know. But I would love to get help in doing this. And the fact that there's a closed source thing that does it, I think, shows that it's possible.
Yeah, it'd be awesome. I mean, it'd be cool.
Cool.
Thank you.
So the performance numbers you showed are basically, I assume, based on like a couple of runs, right?
Oh, sure, yeah.
Yeah.
I mean,
so
they're averaged.
Right. So I was wondering about the startup time, because I assume these files are kind of large. And I mean, the thing that killed, one of the things that killed Java applets was startup time. So is that an issue?
Well, yes. I mean, if you load 10 megabytes of JavaScript code, just the parsing takes some amount of time. And depending on the engine, there are bugs in all the engines about trying to compile code too eagerly, but they're getting better about that, so they don't optimize too early. So yes, there is some startup issue. Probably not represented in these tests because they were all designed to run for a reasonable amount of time. So if a test takes just one millisecond in C, it's not reasonable to compare it to anything. So I think most of these run at about 1 second in C. So startup is pretty much eliminated. But there is some amount of startup issue, yes. And it'll be hard to eliminate entirely.
How viable would it be to, say, use a JavaScript library of GCC compiled with Emscript?
A JavaScript library?
Yeah, like create a JavaScript library with Emscript of GCC, GPG. GPG. I would like to have GPG in JavaScript, and I would like to compile it with Emscript. Yes. How viable would it be to use that in production? Is it fast enough? I mean, this.
I mean, I would assume yes, unless there's some technical detail to the implementation of GPG that I'm not aware of, but it's pretty typical code, right? If they don't use any magical.
So you would go to production with something like that?
I think it could work, yes. I haven't actually tried it, but I don't see any reason why not.
Cool.
Hi, I was wondering what the memory use is like. Let's say I have a 100K library. as a library that would generate 100K of native code. How big does the JavaScript file end up being to download, and how much memory is it going to take in the browser when it runs?
It ends up, after you run it through a minifier, it ends up similar size to the native code, actually. Maybe a factor of 1.5 or so, but it's not ridiculously large. But after you run gzip on it, assuming your website gzips everything, it basically ends up the same size. So in terms of that, in terms of code size, I think it's very comparable to native code. As far as the amount of memory it takes, the amount of memory the compiled code takes, it depends on the JS engine. I don't know actual numbers. The amount of memory taken at runtime, so actually as the slide here shows, there are a few options. Well, I didn't get into almost any of the technical details, but there are a few ways to generate code. One of the ways uses typed arrays with a shared memory buffer, in which case the amount of memory you would use at runtime, again, aside for code, the amount of memory for data would be 100% identical to C++, because you'd be using a typed array that's literally the same thing. So you can use a very similar amount of memory in this as to the native code version.
Hi. So you compile the C. LLVM compiled the C or C++ to bytecode, to
Yes.
LLVM bytecode, and you compile this bytecode to JavaScript.
Yes.
By doing that, apparently you lose variable names, and you have some sort of reverse engineering to do to
Yes.
recreate while loops. Why not compiling directly from C or C++ using Clang or?
Yes, I mean, that was one approach for this. Compiling C directly would probably be pretty reasonable, but C++ is horribly complicated to parse, ridiculously complicated. I underestimate it. You don't want to write that from scratch. It took Clang several years of intensive effort to get to the point where now it can compile most C++ code. So that's simply too much work to do. But second point, by compiling the bit code, you can potentially compile many more languages. If you get Haskell to compile to LLVM bit code, which I believe it can, there's no reason why you couldn't compile that into JavaScript too. So there's also a benefit from that. And third part to the answer, yes, there is a lot of additional work to get back at the high-level data that you lost, but I think we're pretty close to getting there. So it is much more feasible to do that than to compile the C++.
Hi. I was wondering, are you modifying the native code to not depend on integer overflow, or are you actually clipping every integer after every operation?
First of all, it would be better if you would modify the original source code to not rely on overflows, etc. But that's not realistic. So very briefly, to get precise behavior, you do need to do clipping and so forth. And I think I have a slide which mentions a few of the issues there. Overflows, also signs and rounding. Part of the reason why getting optimized code takes time is that the default setting will perform that clipping and sign correction, etc. on every line of code, which makes it very slow. But the optimizer can do sort of like PGO. It can basically run the code, see where it actually needs to do those corrections, generate a profile, and then compile it with that and only perform the corrections where necessary. So the right way to get fast-performing code is either to modify the original source so it doesn't need it, or to do this PGO-like thing, which is a tool that comes with a compiler that basically gets you to the same place. I hope that makes sense.
Thank you.
Thanks.